Hello, this is Barry, Kilowatt United 3 X-Ray. Today I'm going to give a demo on the NanoVNA, and it's not going to be about the antenna analyzer portion of it. It's about using the second port, which is this one, channel 1 they call it, or S21. What we're going to use this one for is to check attenuation and losses. This is something I normally do on a bench type spectrum analyzer, and when I found out you could do it with the NanoVNA, I instantly ran out and purchased one. The one modification I made with the NanoVNA is I put this little SMA male to female adapter on both of these ports. The reason I did that is from screwing in connectors on and off, it tends to wear on the connectors. Well, I don't want to change those, so these little adapters on eBay are cheap, so I put one on each, and when these wear out, if they do, I just take them off and throw them away. All right, well, let's get to making a test. For making tests for attenuation and that, you have to make a set of cables up. Now, you can start out with the cables that come with the unit, which is fine. You can use those. I made my own up, but I'm going to walk you through these. So naturally, you have to use two of these. Another thing you're going to have to do is adapt up. These are on eBay. That's SMA female, and there's their BNC male. You need two of those, and they're on eBay. They're cheap. Another thing you need is these are female BNC at the terminal block. You need two of those, so they're going to go together. You'll need that, and you'll see why in a second. And you will need also an extra 50 ohm SMA terminator, and again, they're cheap. You can get them for like $2 on eBay. Free shipping from China. I don't know how they do it, but anyway, you need one of those, okay? And the last thing you need, I've seen people do it and they use resistors. This is a cleaner method of doing it. This is an SMA 10 dB attenuator, male and female, and in line. And again, you can get them on eBay. This is $7.95 free shipping. This is a cleaner way to do it. So that's what you need. Now, I made my own set of cables, and what I made, let's get this and put this in line. These are longer. I'm sorry if it's blurred. I can't help it. I'm doing the best I can. This isn't Hollywood. So I made my own SMA on one end, BNC on the other end. I go right to here, and this is the arrangement you're going to need for making a test right here. You'll see as I do it. Now, where does the inline attenuator go? The inline attenuator is going to go on the end of the cable, and that is going to go right on here, and there we go. That's what that's for, and that's going to connect to this when we're ready to do it. So the first thing we have to do is turn on the NanoVNA, and we have to do open short load calibration, and we also have to do isolate and through. So that's where the little OSL connectors come from that came with the unit. So I'm going to get this ready, and I'll come back in a second, and we're going to set it up, and I'll show you how to set the Nano up. Okay, now we're ready to set this unit up. First of all, with the cables, I have on one end, here's my 50 ohm 10 dB pad that goes on there, and these cables here, this wire here, that connects the shield to the shield, and this is center conductor to center conductor. Now we're checking for attenuation, not loss. So for check attenuation, first we put those together. Now we're going to do open short. Well, I'm sorry, first we have to set the unit up before we get the open short load. So now what we want to do is set our frequency up. Let's get a little closer here. So we want to set the frequency up. So the first thing we do, I bought this on eBay too. I don't like that little plastic guitar thing they give you. Stimulus is what they call when you get to your frequency. So start frequency is 1 megahertz. Click again. Stop frequency is 30 megahertz. There we go. So now our frequency is set up. Now we want to set up what's called sampling rates. Sampling rates is every time, how many times it takes a reading as it goes through. This doesn't take a reading at every kilohertz as it goes all the way up. It skips. That's the way they work. And now what we want to do is set up the sampling points back. So sampling points, we go to configure, and here's sampling points, and the default is 101 sampling points. We want 401. We want the most we can get to get the most accurate reading. So click on that, 400, go back. Then the next thing to set up is the marker. So we go marker, select marker. We want one marker, that one there, that's it. Bloop, check that one. We can put 2 markers, 3 markers, whatever we want. We only need 1 marker. So that's setting the marker up. The next thing we want to set up is display for trace. So we go to display, we go to trace. Now this has 2 traces. I only want 1, so we'll turn that one off. Now I'll turn that off to start from 0. We want trace number 1 turned on. Now we go back, and after trace, we want to set up what the trace is going to read. Do we want it to read SWR? What do we actually want the trace to read? So we want to go to trace again. We want to go to format. Here's Smith chart. Here's SWR. We want log mag. Log mag is going to show dB. So now that's log mag. So now that's set up. Now we want to do channel. There's 2 channels on here. Channel 1, channel 2. Channel 1, channel 0, channel 1. I'm sorry. Channel 0, channel 1, or S11 or S21. So channel 0 actually sends the signal through the unit, comes back here, and channel 1, S21, is the receiver. So we want to know, we want to make sure it's set on channel 0 right now. So we want to change that, and we want to go to channel. So we go back, and we go channel. Channel 0, we want channel 1. So now that's channel 1. Now that's what the display is going to read, channel 1. So we did frequency, and now we're set up for OSL calibration. Now we have to calibrate the unit. By calibrating it, what we're doing is the final reading is going to be taken here, and we're going to cancel all this out and make it transparent for taking a reading. So the first thing we need to do is go open short load calibration. So we got a little barrel connector that came with it. Put the barrel connector in there. We're going to need it. We're going to put open on the barrel connector at the end. Now make sure you do it on the right end, okay, where the attenuation pad is. So now we go back, we go to calibrate, and there's calibrate. Calibrate, we're going to do open. Now as you take notice, open doesn't have anything there. And what you're going to see when I tell it to go is going to be a blue line going across here. So I'm going to zoom in. Oh, I am already zoomed in. And let's see, open. Okay, now that blue line is going across. I don't know if you see it, but watch. There we go. Opens a check mark. It's ready to go. So now we put the short on. So that's open. Now we do the short. Tap it. Here's our blue line. Bloop, bloop, going across. That's going to change. There's a check mark. We did that. Load. Check that. Now we go to isolate. Now isolate is where we use the second SMA load. Now if you don't have a second one, you can still do it. You can take this one off and you can put the open on this end. Now be careful, that's what I'm saying. The 50 ohm goes here and the open goes here. But it's more accurate if you use a 50 ohm on here, which is what I did. So now we do isolate. Now the next thing we're going to do is through. The through calibration on a spectrum analyzer, it would be called normalize. What it's going to do is set up, let's get this off of here, get this off. This is, come on, get on there. See how many times you go on and off on these connectors? Eventually they're going to wear out. Come on. There we go. Okay, that one's on. Now we're going to normalize. You see where this reading is? We're going to make that go right to the 0 line. So now we do through. That's done. Still there. Now once we hit done, see the line? right up to 0. So now we're ready to take readings. But we may want to save that first, so every time we do this test, we don't have to keep setting the unit up. So let's go and save configuration. And recall. We don't want recall, we want to save it. Calibrate. Calibrate. That was done. Oh, here we go, save. We want to save it at 2. So now that's saved. So every time you want to do this test, and when you turn this unit on, it goes back to 0. Save 0. Whatever you have in save 0, when you turn the unit on, it goes to that. So now all you have to do is turn the unit on, go to recall, and hit 3, and you're ready to go. So now the test is ready to go. So now what we're going to do is, go back. Now we get this. Let's get these out. So now we get this guy here. And here's where we're going to put our device under test, right here. Now this is an FT 240-43 core. Now whether it's, see now you're only testing one leg, whether you have coax or wire on it, you're going to get the same results. Because what you're going to do is, if you had coax on it, you're going to connect this to the shield. Because you're looking for attenuation. You're not looking for insertion. You're looking for attenuation. So that goes there. Okay. So from now on, I'm not going to keep zooming out and in. That's how we're going to be doing our test. So we'll lay that down there. And then let's go back and let's zoom in so we can get our readings over here. So now, if you read closely, I'm going to move this. There we go, up on top. I want you to see that. So now I'm moving the marker, and I'm moving all the way down. And now we're going to go to 1.8 megahertz, 1.5, 1.652. Now, if we didn't do the sampling points, it goes from 1652 to 1725. If we left that sampling points on 50, it'd go from 1652 probably up past 160 meters to 2.0. It would skip that. So that's why you want the 400 sampling points. So now what we have is 1.870 megahertz. You have 28 dB of attenuation. Okay? 28 dB. Now that's at 1.870. Now I marked that down because I'm going to show you what a 31 core does, how this whole sweep will shift down. So we're at 28 dB of attenuation. Now the benchmark for a good balun is 20 dB of attenuation. That's not to say when it's 19 dB of attenuation, the balun no longer works. Yes, it still works. It's just that it's starting to lose efficiency. It's not doing its job. The lower the number, the worse it'll get. And it'll get to the point that it's not doing anything, which I'm going to show you. And the RF can actually come right back down the transmission line to the radio. So just remember, your benchmark is 20 dB. So what we're at right now is 28 dB. Pretty darn good. So now we're going to go up in frequency. And we're going to go up to 30. Here's 35, 37. So here's 80 meters. And that's 32 dB of attenuation. Darn good. Now we go up to 40 meters. 70, 72, 35. That's good. 36 dB. Darn good. 30 meters is 38 dB. 20 meters. Close. Skip by it a little bit. Come on. There we go. That's 38 dB. This is an outstanding choke. Here's 15 meters. 15 meters is 36 dB. And look at the top at 10 meters. 30 megahertz. 31 dB of attenuation. This is an excellent choke. Some people say you can't get a good balun to go from 10 to 160. Yes, you can, and here it is. Now I'm going to use the 31 core. So for people like to focus on the low bands, you could use the 31 core. And if you really just want to use 160 meters, you use I think it's a 77 core if I remember, 75 or 77. I think it's 77. But anyway, here's 30 megahertz. Here you're at 26 dB. Now I'm not going to go through all of them, but let's go all the way down to the bottom of the band again. You can see how the whole the whole sweep, shift it down because of the 31 core. Now let's get 18, what was it, 1870. Here's 1870. 18, no, that's, it's 12, 7, here's 1870. Now 1870 is 33 dB of attenuation. Now if you remember the 43 core, it was 28. Now we're up to 33 dB of attenuation. So as you can see, what it's doing actually moved down, so you have a better one for 160 meters. Now if you use a 61 core, now that peak here would be up around here, around 20 meters. And it would drop off, and if I remember correctly, 61 core wouldn't even work right on 160 meters. I think it could sneak in 80 meters, surely 40 meters, but on 160, it didn't work. Now here's another core. Now this is a smaller one. This is an FT 140-43. Now this one only has 12 turns on. So if you make a balun and you use RG316 on it, this is an excellent, excellent one. So as you can see, on 160 meters, it's 22 dB of attenuation, which is good. And you can see it goes down, and now we're above 30 dB all the way up to the top of the band. It's actually 32 dB to 30 megahertz. So again, it's a really, really good balun. And if you want to do better on 160 meters, you put 2 more turns on there and it'll shift it down. Now people, you see them on YouTube, they use a powdered iron core. This is a T200-2. Powdered iron should only be used for making inductors. That's what they're for. They're not for baluns. They're not for ununs. You use ferrite for ununs. And this is 12 turns on a powdered iron core. Now look what you have. 160 meters. Let's see what we have. 1870. 0.48 dB. 0.48. That's nothing. That doesn't do anything. That's worse than an ugly balun. I think an ugly balun gives you more, but an ugly balun is not broad-banded. And for you people that like to use ugly baluns and think they're good, I'm not going to do it here. I've done it already. Do your test on your ugly balun. You can see how pee-poor it is. They don't hit 20 dB of attenuation. So the best it ever gets for using powdered iron is, here's 10 meters, 28.2, and that's 12.9, 13 dB of attenuation. It really doesn't do hardly anything. So that's why I say you never use powdered iron for a balun. One guy built one on YouTube. He showed it. He used bifilar turns of wire going around. Because of the spacing on a bifilar, there was so much reactance and impedance was wrong on it. SWR was high, and it offered no attenuation at all. So you don't want to do that. Now, the one thing I do want to show you is when it comes time that you want to check a balun for insertion loss, or if you want to check a 2-position or 4-position antenna switch for isolation between ports. You do your OSL calibration, and instead of using these wires in this setup, what you do, let's take these guys out of here, and you want to put a barrel connector in line, okay? So now you put your barrel connector in line, and now what you do is you do your calibration all over again, and that'll zero out. And now when it comes time to test, you take your barrel connector out of line, and you get your balun under test, and now you're going to see you're checking both shield and the center conductor. So you put it in line like this. Now it's in line, and now you run your test. Now you're checking for insertion, and now it's going to show what the insertion would be for this. Now this isn't calibrated right because I calibrate it with, using these guys, so what reading you're getting right now is not good. And if you want to actually see what this is for insertion, I can show you. I'll go to recall, and that would be 3. Look at where the line is. It's right on 0. What you have to do here to get a real reading is you have to change from 10 dB per line. You have to change it to maybe 2 dB or 3 dB, and you can do that, and it'll show you a little bit of insertion. As you see, you get up to, let's see if it reads it here. It'll still read it, it just won't show you. Here at 30 megahertz, the loss on this balun is 0.19 dB. I guess you can't see that. Let's zoom in here. There. Now, it doesn't show it good visually, but it'll still take the same reading. It doesn't make any difference. So the insertion loss on this right now at, we're up to 148 megahertz, is 0.19 dB. Now, this isn't going to work on 2 meters. It just happened I set this up for other tests. So let's see what it won't work for that because the insertion's not bad, but because the ferrite is the wrong material, the attenuation is not going to be there. But it will be good for 10 meters. So let's go down to 10 meters and see what it really is. So here's 26. Here's 10 meters right here. 29 megahertz. Now, the insertion, the loss on this is only 0.08 dB. That's the loss by putting this line. You're not going to see that on any S meter. So that's good. Now, the attenuation, I'd have to take this apart and put the clips on again, and go this way. But I just want to show you. So what you would do is put a 2-position antenna switch in here, and you put it to through. And when you put it to through, you'll get your reading, and it'll tell you what the insertion loss is, okay? And then when you turn that switch to the second one and don't move your connectors, now it's going to show you isolation between ports. And then you're going to see if it's a good one like a Dewa or an Alpha Delta. Alpha Delta, you'll see about it'd be 50, 60, maybe 7 dB of attenuation between ports, which is really, really good. So that's how you use this to check. And I have a spectrum analyzer to do that, a bench type, and that's expensive. So when this come out, I couldn't pass it up. I could almost get 2 of these things. But this is a 4-inch display, and it's really a good unit for the price. You have to watch on the internet. There's a lot of knockoffs. So be very careful when you get it. I'm not promoting a business. What I'm telling you is I bought this from R&L because I knew they had the right one. And wherever you get it is fine, but make sure you get the right one. Don't get a knockoff. I've seen on YouTube videos where people did. You couldn't calibrate them right. You couldn't do anything with them right. Some of them are really, really bad. So there's your demo on how to set the unit up and how to actually make tests. Good luck. 73 did it from KU3X.